There are three forms of equations of lines that are going to be really useful. First is the slope equation, then slope-intercept, and finally point-slope. So let's start by finding the slope of the line that goes through -3, 4 and 5, -2. One way to do this would be to graph the 2 points and then look at the horizontal and vertical difference between the 2 points. Looking for the rise, that's the vertical difference, and the run, that's the horizontal difference. We could literally count those on the graph and notice that we go down 6 and to the right 8 to get from the left point to the right point, which gives us a slope of -3/4. We could also use the slope formula to accomplish the same thing. We just have to decide which point is point 1 and which is point 2, and it doesn't make any difference. So we'll use -3, 4 as the first point and 5, -2 as the second point, and substitute those values in the slope formula. Once we simplify, we can see that we get the same result, a slope of -3/4. Now let's use those same 2 points and write the equation of the line in point-slope form that goes through those points. This is what point-slope form looks like, and to use it we need to know a point on the line and the slope of the line. We've already found the slope of this line. We did that in the last problem. And we have 2 points on the line, so we just need to pick one of them. I'll go with the -3, 4, but either point will give you the same equation. We'll substitute -3/4 for the slope, and we'll substitute -3 for the x sub 1 and 4 for the y sub 1, and when we do that, we've got the point-slope form of the equation. If we want to write that equation in slope-intercept form, that's y equals mx plus b form, we just need to do a little bit of multiplication and rewriting. So, for example, inside the parentheses, x minus -3 is x plus 3. We can distribute the -3/4 on the right side of the equation and then add 4 to both sides to get our slope-intercept form. Now let's look at some ways to graph a line. We're going to look at 2 methods. The first is to use the slope and the y-intercept of the line. And in order to do that, we need to take the equation that we've been given and write it in slope-intercept form. So the first thing we'll do is subtract 2x from both sides of the equation and then divide both sides by 3. Now we've got the equation in slope-intercept form. So we'll start with the y-intercept, which is -4, and use that to find a point on the line. Since the slope is -2/3, if we go down 2 and to the right 3 from that point, we find our second point on the line, which gives us enough information to graph the line. The second method we could use to graph the line is to use intercepts. To find the x-intercept, we'll substitute 0 in the equation for y and solve for x. So our x-intercept, where the line crosses the x-axis, is -6. To find the y-intercept, we'll substitute 0 in the equation for x. And when we simplify that, we can see that the y-intercept, where the line crosses the y-axis, is -4. Now that we've got 2 points, we can graph our line. Let's use that same line and write an equation of a line that goes through the point 4, 2 that's perpendicular to the line 2x plus 3y equals -12. Here's what that line that we're looking for would look like. We've got the point 4, 2, and a perpendicular line to the one we just graphed would be at a 90-degree angle. So the blue line is perpendicular to the yellow line. If you have to write an equation of a line that's either parallel or perpendicular to another line, you need to know 2 things. First of all, parallel lines have equal slopes, and perpendicular lines have slopes that are opposite reciprocals. We just went through the steps of finding the slope of the line 2x plus 3y equals -12, which was -2/3. We want to write the equation of a line that's perpendicular to that. So we need to find the opposite reciprocal of -2/3. In other words, flip that to -2/3 over and change its sign. So a perpendicular slope would be 3/2. Now that we've got the slope of the line we're looking for, that's the blue line, and a point that's on the blue line, we can use our point slope formula to find its equation. We'll substitute 3/2 for the slope and 4 for x sub 1 and 2 for y sub 1. That's the equation in point slope form. If we want that equation in slope intercept form, we'll simply do a multiplication and then add 2 to both sides, and we have our equation in slope intercept form as well. Now let's look at 2 points on the graph, but let's do something a little bit different. We're going to find the distance between these 2 points, -2, 1 and 4, 9. The distance we're looking for is the length of that red line segment, and we can actually use the Pythagorean theorem to find it. The Pythagorean theorem relates the lengths of the sides of a right triangle, and although you may not see one, there's one there if we think about rise and run, just like we did when we were finding slope. The hypotenuse of the triangle, that's the length we're looking for, is C, and the sides of the triangle, the A and the B, are the rise and the run that we see in the picture. Now we know how to find rise and run. That's a change in x's and a change in y's. So that's really what we're using to find the lengths of sides A and B. We'll find the difference in our x coordinates of the points and the difference in the y coordinates of the points. When we simplify, we'll see that c squared is 100. But we want to know c. That's the length of the hypotenuse, which is the length of the line segment we're looking for. So we'll take the square root of both sides of that equation to get the length of c, the distance between the 2 points, as 10. Now let's stick with those 2 points and that line segment, and let's find the midpoint of that line segment. The easiest way to remember how to find the midpoint is to think of it as averaging the x coordinates and averaging the y coordinates. So the x coordinates are -2 and 4. If we average them, we add them together and divide by 2. And the y coordinates are 1 and 9. If we add them together and divide by 2, we get their average. So that means the midpoint of this line segment is the point 1, 5. Next, we're going to look at how to graph a circle when we're given its equation. The equation of a circle in standard form is the quantity x minus a squared plus the quantity y minus b squared equals r squared, where the center of the circle is at AB and the radius of the circle is r. Let's see how to find that information in the equation that we've got. We need to think of the y plus 2 as y minus -2, so that it looks like y minus b, and we need to think of the 25 as 5 squared. So now we can pull out the information we need. The center of the circle is at 4, -2, and the radius of the circle is 5. Now here's how we use that information to graph. First, we'll graph the center of the circle at 4, -2. That's not part of the circle, but it will help us find some points that are on the circle. Because the radius is 5, we can go up 5, to the right 5, down 5, and to the left 5 of the center to find 4 points on the circle. And once we've got that, the circle is easy to graph. Now let's take a quick look at functions. A function is a relation in which each domain element maps to exactly one range element. And there's lots of ways to represent them. We could represent them as ordered pairs, or as tables, or as graphs, or even as equations. We're going to look at a relation that's expressed in ordered pairs and ask ourselves, is it a function? To answer that question, let's look at the domain and range of this relation. The domain is the set of all x coordinates. Those are like input values. And the range is a set of all y coordinates. Those are like output values. Now let's map the domain elements to the range elements. 3, 4 is one of our ordered pairs, so that means 3 maps to 4. 2, 1 is another ordered pair, so 2 maps to 1. 5, 1 is an ordered pair, so 5 maps to 1, And 1, 6 is an ordered pair, so 1 maps to 6. So is it a function? Yes, it is. The reason is every domain value maps to only one range value. 3 only maps to 4, 2 only maps to 1, 5 only maps to 1, and 1 only maps to 6. Now let's answer the same question for this relation. Is it a function? And we'll also take a look at what the domain and range are and how they map from one to the other. The domain is a set that contains all of our x values, which are 3, 2, and 1. And the range contains all of our y values, which are 4, 1, and 6. Now let's do the mapping. 3, 4, 2, 1, 3, 1, and 1, 6. This relation is not a function, and it's because of what's happening with the domain value 3. 3 maps to both 4 and 1. So we can't say there's only one range element that matches up with the domain value of 3. That means we don't have a function. Now let's go back to our circle and ask a question about it that's related to something we just said, which was the domain is all of the x coordinates, all of the input values, and the range is all of the y coordinates, all the output values. And the question is, what's the domain and range of this relation? Well, if the domain is all the x coordinates that we see on our circle, the domain is all the x values from -1 to 9, including those values. And the range is all of the y coordinates from -7 to 3, including -7 and 3.